Actually, I have changed my the title a little bit because I don't think I'm ready enough to talk about something about the anomalies. So I will talk about the title of the talk is
just push the
control
button
plus
side of the
control plus
computer will don't use the fancy functions if you don't know.
Control plus L.
Yeah.
Control plus L.
Hesitate.
Control L
Good.
So I'm going to talk about the generation of quasiparticles by particle-antiparticle mixing and the limitations of quantum mechanics. And so this is about my upcoming paper, one paper or two papers, which will appear on arXiv very soon. So basically, the contents of the talk is consists of two parts. And in the first part, I will talk about some limitations of quantum mechanics when we have some particle-antiparticle mixing, and I'm talking about the mixing of some unstable particles. And the second part is then what can we do in the quantum field theory. That's what I'm going to do. Let's first talk about the mixing in quantum mechanics. As you know, the standard way to describe the particle-antiparticle mixing is to go to the quantum mechanics. And this is the Schrödinger equation for such a mixed system when you have mixing. So here, pi denotes something like measure, so something like B0, and pi star denotes something like B0 bar. And this is the effective Hamiltonian, and it is given by this formula. It is given in terms of a self-energy of the heavy particle. So usually we diagonalize the effective Hamiltonian, and so this is the mixing matrix which diagonalizes the effective Hamiltonian, and we get some final form of like this. Here, P is the kind of it consists of the mass and the total decay width. And after solving this equation, we are supposed to get so for mass eigenstate, we get this solution. So this is just here. This is what is so-called mass eigenstate, and it is always a fixed linear combination of the basis states. And it's fixed in time. And this is a time evolution part. So we can write it in this way. So this in the same frame, it can be written in this way. This is the core mass, or the physical mass of the measure, and this is the total decay width. So we have so this is the plane, the time evolution part of the plane wave, and this is the damping factor. So this part the decay of the measure, the particle. And as you know, this is the thing which corresponds to the propagator in the quantum field theory. We can just Fourier transform this to obtain this. And so what I'm going to say is that actually this description misses something. That's what I'm going to say. And so I'm going to go to the quantum field theory description of the particle-antiparticle mixing. So what I should do is to what I'm going to do is to obtain this kind of structure by diagonalizing the Resummed propagator. That's basically the plan. So how can you calculate the Resummed propagator of the heavy particle? So this is just standard procedure. We do this is the notation for the Resummed propagator, and we do some geometric summation using at a matrix level. So here m pi is the tree-level mass of the measure, and this is the self-energy. Actually, I times this is the self-energy. And after the geometric summation, we get this expression. And so this, when we have mixing, this Resummed propagator is in the matrix form, and defining first we define phi1 as pi and phi2 as pi dagger or pi star. They are identical. So, so each component of this Resummed propagator means this kind of thing. So, for example, delta 1 means pi goes to pi, and delta 1 means pi star goes to pi. So here there's definite direction of the energy transport. So I mean, 1 2 is not the same as 1 in this Resummed propagator. So okay, so what's the next step? The next step is, of course, so as I said, I'm going to diagonalize the propagator. And it turns out that the mixing matrix which diagonalizes the self-energy, so this is diagonalized self-energy. So the same mixing matrix diagonalizes the propagator, the Resummed propagator. And this is the diagonalized Resummed propagator. And it has this form. And here P is a diagonal matrix, which given by, whose component is given by this. So this is the diagonalized self-energy. So what is important here is that this matrix C is non-unitary. That's because, as I said, I'm talking about unstable particles. So the self-energy always has the absorptive part. Mathematically, it's skewed Hermitian part. So because of that, this is never Hermitian. So it cannot be usually it cannot be diagonalized by unitary matrix. So in general, the mixing matrix is non-unitary. This is important. So if you are thinking about the mixing of stable particles like the mixing of light neutrinos, it's nothing to do with what I'm doing now. I'm talking about the mixing of unstable particles, and in that case, the mixing matrix is non-unitary in general. And after we diagonalize the propagator, what we do is expand the diagonalized propagator around the pole. So this is the pole of the propagator, and this is the pole mass, and this is total decay width. And here R denotes R is the residue of the propagator, but usually, and it's in the, I will set it to 1 because in the, I will calculate of the one loop order in the self-energy, and up to that precision, you can always set it to 1. And as I said, this form of the propagator is what is something corresponding to this time evolution of the plane wave with some damping factor. So the degree of freedom, which corresponds to this, the component of diagonalized the propagator, has this time evolution. So everything up to here is standard. Everybody, so many people are familiar with all these steps, and everything is standard up to now. So what can be something new? So let's go a step further. Now we write this is now non-diagonal before the Resummed propagator before diagonalization. And this is the component of diagonalized propagator, and these are the mixing matrices. Now I have evaluated at this mass because as I did the pole expansion, so which enforces this matrix to have so I have to use this matrix. Okay. So the non-diagonal component of the Resummed propagator can be written in this way. Now we take its Fourier transform. Then the corresponding correlation function will be this. So now, as I did before, I'm using this notation, and this is a kind of compact notation for the correlation function. Here, for example, pi2 dagger means pi, and so all the components can be written in this compact way. And this should be actually time ordered correlation function because, as I said, there's a definite direction of the energy transfer when you define the component of the solution propagator. So let's go one more step. Now we diagonalize this matrix, and using this relation, then we get this relation here. And here, now, this pi hat I is defined by this, and pi hat f is defined by this. So now they are, as I said, they are non-unitary matrices. So which means that this pi hat I is not the same as pi hat f. Only when they are unitary matrices, they are identical. And if we can also calculate this part in a straightforward way. It's just simple Fourier transformation, and its time part is this in the same frame. So this means that this is the correlation function related with this time evolution part of the free particle. And how can we interpret this? This means that actually the particle of the degree of freedom that corresponds to this diagonalized component of the propagator is something like excitation of this field. It emerges as an excitation of this field, but ends as an excitation of this field, and they are different. So something very non-standard is going on. So now let's go back to the quantum mechanical description. So whatever we do, I mean, what we do is nothing but the diagonalization of this equation, and we always get this kind of equation. This is the effective Schrödinger equation for each mass eigenstate. And if we solve this equation, we always get this solution. So this is a time evolution part, and this is fixed part, and this is some fixed linear combination of basic states. So, but as I said, we cannot relate a single fixed linear combination of basic states to this propagator. It's what is actually happening here. So which means that the conventional quantum mechanical description cannot be a proper relativistic limit of the quantum field theory when you have the heavy particle and particle mix. So whatever we do in the quantum mechanics, we get this solution, but it cannot correctly describe this result, which is obtained from the quantum field theory. So that's why I'm saying like this. So this means that we have to find a way outside quantum mechanics to describe particle-antiparticle mixing. And so basically the strategy is to read the decay rates from the scattering mediated by actually I think I missed one thing. So yeah, so because of that, this is something, the particle corresponding to this degree of freedom is something non-standard. So it requires an interpretation like a Quasiparticle. So this is very common in the solid state physics. So it's a kind of emergent phenomenon generated out of the interactions in the theory. So this interpretation is mandatory. So what I'm going to do is to read the decay rates from the on-shell Quasiparticles. So okay, so for that purpose, I'll just briefly explain what the program. Basically, I introduced some toy model to simplify the analysis, and this toy model mimics the real Mason system, neutral real Mason systems, neutral scalar Mason system quite closely. And here, I'm only showing the interaction terms here, and this interaction term. So here, I introduced some light fields to C and chi and Cuisine. So I introduced some 3 fermionic fields, and pi still denotes the measure. And this term introduces mixing between the measures, and this term can be used for tagging the states, because this combination only couples to pi, but this combination only couples to pi star. So we can use this interaction for tagging. So the basic step is to calculate some transition rate, which I denoted by this, and the basic procedure is to calculate. So, for example, when I'm thinking about the final states, I will, for example, consider this final states. So, let's draw a diagram, final diagram, which begins with this final states and also ends with the same final states, and draw such a diagram and apply some unitary cut. And in this procedure, this unitary cut will give the all possible initial states that could generate the given final states I chose. So, I mean, using this diagram and applying unitary cut here and apply this phase space integration using this delta function. Here, it turns out that this transition rate, the sum of all these transition rates is equal to the sum of the total decay risk. As you know, this total decay risk comes from the imaginary part of the pole. So we already know this after we diagonalize the propagator and after we expand the propagator around the pole, we get this total decay risk right away. But it turns out that this is obtained in a different way, and it turns out that they are identical. So, for example, if you want to know the partial decay width from for each Quasiparticle, then it's actually tempting to remove this summation of alpha and take sum over only x, then it should give some partial decay width, which about the decay product y. But we want to do that actually to define some partial decay width, but actually it's not always possible because that quantity is actually generally a complex number, so it cannot be interpreted as a physical transition rate. So we need this in general, we need this summation is always well defined. So okay, so I got some quantity. I wanted to find the partial decay width out of it, but actually it doesn't always work. So, but NHD is related to the decay width, total decay width. So I got some useful quantity. So now how can you define the partial decay width out of it?
How do you verify numerically?
Yes.
Numerically confirm that. What do you mean?
I checked a lot of different. I mean, I'm using some tone model. So I chose a lot of different input parameters and checked the identity, and they are always identical up to the precision I'm working.
Can you do just analytically, because you have
no.
when you can and calculate all the decay ways. Partial with according to the usual quantum field theory.
No, I will explain it.
We won't have time.
Okay. So let me first define the partial decay width in this way. So here now we tag the initial state using these interactions. So now this will give pi, and this will give pi star. So this is my definition of partial decay width. And actually, it turns out that it is consistent with some well-defined formula everybody knows when there's no mixing. So so let me explain. So you might think that why don't you calculate this? So there is a well-known textbook formula. Why don't you use this formula to calculate this quantity? Okay. So but actually this formula only works when we can neglect the mixing effect. So for example, when we have only vortex loop correction, or when we consider only two-level calculation, this works. So for example, if you want to add self-energy diagrams like this, then it turns out that, and send this initial state on shell, that's the meaning of what this matrix element, the initial state is Longja, and it turns out that this sum vanishes. So actually, in this way, you cannot correctly, actually there's no way to correctly calculate in the quantum field theory. There's, in the textbook calculation, there's no way to correctly consider this mixing. That's why we need some complicated way to define partial decay list in a different way. And one important difference is that now these initial states are official, because what is, in this calculation, what is really on-shell is the Quasiparticle. Okay, so actually it turns out that there's sometimes there's a big difference between the cavity description and claim description, but not always. As you know, the particle-antiparticle mixing is very well tested in experiment, so you will think that there must be something wrong in my equation, but actually not. Actually, even though there are some difference, in many cases they are identical. Actually, that explains why we couldn't see the difference in the experimentally tested results. But sometimes the results actually shows that sometimes there's a large difference, especially when some interference is involved here. So this is a conclusion. And this is just a summary of what I said. And about the last one, actually, the original motivation to do this is to how to. There's a very well-known problem in the Majorana physics. I mean, several different groups got different formulas for the CP asymmetry. And that problem, I mean, they are all different. So, and that problem has not been resolved yet. I mean, it has been in the research. I mean, that problem existed for like 15 years. So, and using the method I developed, this problem can be also solved. So, and that was actually basically my original motivation to derive all these things. And I'm working on this. Thank you.
Any comments?
Well, I think you're doing things probably inconsistent, because then all this calculation is a perturbative calculation. So you want the one part you are summing over all this some loops, and then on the other part, then you are just doing perturbatively. And then what do you mean now? They see all this you seems to want to sum over everything, but then at when you do the calculations, all this perturbatively. You know, do order by order, each order.
No, I'm doing everything very consistently. I mean, for example, so when I said
Discussion later on. So we thanks for all the speakers in these sections. And anything more to say?
Well, we just maybe wait a few minutes and go to the toilet. Okay. Then we will go to the speakers and chairs. Go to the